Now we still have a little time for our first speaker.
Ready? Ready? Yeah. Thank you very much, Professor. Thank you very much, Professor Tang. First of all, let me give felicitations to the leadership of ISEG. She been the president of ISEG, and so Tang, the Secretary General, for an excellent event or a series of talks that have now been organized and will happen for the next 2 days. I am very impressed personally, and I also say welcome to my fellow speakers. I have seen a good array of all the speakers, and they will soon be ready to speak. So I will not take too long, because I know that many others will need to speak too. So I'll keep within my time. My presentation, which should be up now, is entitled Improvement in Rock Trenchability for Lifelines and Energy Storage Chambers in rock. The reason for this, the rationale for this type of work, which is in the area of rock mechanics and geoenvironmental engineering, is there are three main utilities for mechanical excavation of rocks. The first one is laying of communication cables to improve ICT infrastructure. As everybody knows, we are currently in the information age, and there is the need to lay infrastructure. And in many places in the world, the terrain is rocky, and the trenches need to be cut to lay those cables. The second one is that oil pipelines crisscross many parts of the world, and oil is still being discovered in many places that are over. You see, this is a typical excavating machine. That excavation machine has a boom. That boom is the portion that is buried in the rock. There is a chain, and that chain bears some cutting bits, and those cutting bits dip into the rock and cut it. So this is the rock mechanical aspects that we are now going to talk about. Next, please. Next, please. Next, please. Okay, so our interest is that if you look at this free body diagram, this is a representation of the boom of that machine. There are cutting bits on the chain, and the cutting bits on the chain extend and then run around on the chain and rip into rock, and then will dislodge fragments from the rock. As they dislodge the fragments, the trench is advanced into the right direction. You see, on the ground surface, I've written an arrow there. That arrow shows the movement of the boom to cut the trench. Next, please. Next, please. Next, please. Okay, next, please. Okay, so geomechanics of rock cutting, which is section B. So we are now going to look at the geomechanics of rock cutting. Now, if you look at one of those bits that I showed earlier, that bit, I have now drawn the free body diagram of it. The free body diagram is a representation of the orientation of the cutting bit with respect to the rock material. I have shown that this cutting bit has to penetrate the rock and then remove a fragment that is approximately from the shaded area. So the fragment would come from the shaded area. If we look at the boom of this machine, that is the arm that was extended into the rock. On that chain, there would be cutting bits that look like what I have just shown. Now, the spacing of those cutting bits, those cones, is very important with respect to cutting efficiency. And in cutting, there is the parameter we call the specific energy. That is the amount of energy that is expended to remove a unit volume of rock. Our interest is to reduce the specific energy in cutting, because the specific energy can be a very good measure of the efficiency of cutting. Now, the arrangement of those cutting bits on the boom are very significant. There is an optimum spacing of those cutting bits, and that is the second, if you start counting from the left. The second spacing that you see there demarked by W, it is demarked by W. It corresponds to the minimum specific energy. So in rock bit interaction, rock bit geomechanical interaction, it is very important to optimize the spacing of the cutting bits. Next. 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 It is tough. Next, please. Okay. Now, another parameter that is very important with respect to rock cutting, another parameter that is very important with respect to rock cutting is the existence of cracks. When cracks exist in the rock, it means that large fragments can be reduced, can be removed. The removal of large fragments results in low specific energy. So in 1990, I developed this theoretical, or what I would call phenomenological pattern that shows what typically happens when we have that rock bit penetrate the rock. There were many other theories before my own. For example, in 1957, Fayhurst and Lackaben, they were at the University of Minneapolis, University of Minnesota in Minneapolis, St. Paul. They were very deep in mining. So you see their theory top right, when a tool cuts rock and how the fractures will radiate. And then Hartman in 1959 also had his own. You see that the cutting bit does not touch the cutting surface. As a result, there's reduction in friction. Then the one at the bottom to the right was made by Whittaker and Shulsky. They were very, very excellent researchers in rock mechanics. You see, in their own case, the implication is that cracking, a crack that radiates at the tip of the tool, creates a chip by that crack running to the surface of cut. And then there were others like Coates in 1981, Coates that you see there in the middle to the left. In his own representation, the cutting bit just dislodges, it wedges, it dislodges the rock so that it creates that chip. In my own case, the cone does not need to penetrate to the depth of cut, meaning that you don't have to expend a lot of energy, but that is promoted by the existence of cracks. So how do we then improve rock cutting? If we can have a system in which we can induce cracks in a material before this cutting bit acts on it, it means therefore that we can reduce the required cutting forces. We can also reduce the required cutting energy, and machines would be able to cut very fast, cut those trenches very fast in rock. Next, please. Next, please. Next, please. Next. Okay, now, there are many, many factors that we need to consider in the modeling process. This figure that I'm showing here shows what typically happens if we would plot the relationship between the cutting force, the penetrating force, that we press this bit into the rock surface, and the distance. Typically, because of the existence of cracks, we would not have what we would typically have in the deformation of other materials, in which this relationship between force and distance of penetration will be rather smooth. If we had a plastic material, this relationship would be rather smooth. But because the rocks near the ground surface, where trenches are constructed, tend to be very brittle. They are brittle because of fatigue. In the daytime, they will be hit At night, they might be cool. And then you have wet and dry conditions that cause cracks to develop in superficial rocks. As a result of this, most superficial rocks tend to be very brittle. They are brittle and they can be acted upon by the action of cutting bits. And when that happens, if the force, the displacement relationship is plotted, it tends to be this wavy, as I've represented. So typically, when that cutting bit moves across the cutting surface, it will dislodge cracks, as I've seen. You see LP, that's the first one. When once that crack travels to the ground surface, that fragment L is removed. The next one, the bit re-engages with the rock and creates another fracture, and so forth until several fractures are removed. In doing this, energy is expended. And my concern now is how much energy is expended. How can we integrate that energy that needs to be expended to create these fragments so that the cutting rate will improve? Because cutting rate is essential, an essential parameter in the determination of trenching cost. Next, please. Next, please. Next, please. Okay, this is merely a representation of the cutting bit that I made some years ago about how if the cone is oriented in a certain way, it results in the size of fractures. So we can work out the trigonometry of this, but I don't want to spend all the time on working out the trigonometry. Next, please. Next, please. Okay, now our interest is this, that as we now have information on how the phenomenon works, we need to go to the mathematics of it, because it is the mathematics of it that enables us to estimate the required cutting energy. What is the horsepower requirements of that machine? So in 1990, I developed this relationship between the depth of cut and the force that needs to be put on each cutting bit. So I will not go through all of the mathematical integrations, but what I want to show is that there is that relationship between the cutting force and the depth of cut, the depth to which the cutting bit penetrates. Of course, my energy is to convert that force. Okay, my interest is to convert that force to energy. And energy is equal to force times distance. Energy can be determined as force times distance. So we have the energy that we give each bit, and we know the number of bits. It is possible to compute the total energy supplied to the bits by adding them up, and then looking at the machine itself, how it generates the angular momentum to run these bits on the surface. And then from there, we will use trigonometry to calculate the horsepower requirements of the machine to cut certain trenches at a certain speed. So that's why you have that LR there. Let's go to the next slide. Next slide, please. Next slide, please. Okay, so in this case, you see that FC is the average cutting force. I've already shown earlier how this average cutting force works. That is, the bit will now be loaded and it carries a certain force over a certain distance, dislodges fragments from the rock surface, and in so doing, expends energy. So if we have the number of bits that are in contact with the rock surface at a particular time, it is possible to calculate the total energy requirements and then use that energy requirements to calculate the cutting rate of the machine. Now, I have just indicated earlier on that the presence of cracks in rocks makes it easier to cut those rocks. Second, the energy reduces, the energy requirement. The speed of cut also increases as a result. So how do we then create a machine that is able to create cracks in rocks before the cutting bit comes in contact? This is something that I worked out with a number of my co-researchers a few years ago, and we are still working on this. So the next section deals with how we can apply impact loads while at the same time cutting. The purpose of the impact loads that hit the surface of the rock is to create cracks on the rock surface, while the cutting bit then comes to action. And its action will now be with much reduced force because it doesn't need a lot of force anymore. The rock is not as intact as it was before. Next, please. Next, please. So essentially, a pointer to these kinds of things. Please go to the earlier one. The earlier one. Just go to the earlier graph. The earlier graph, one before this. Yes. This is not my own graph. Somebody else did this work in 2013. Next, please. The next one. The next one. The graph, please. This work here was done by Pastarus and a number of other. No, please let it stay. Earlier. Go back, please. The system is okay. This is fine. Leave it here. Leave it here. The system is unstable. Okay. So next, please. Next, please. We'll go back to using. Okay. You see here, there is a point load index and fracture spacing. When fracture spacing in a material is very large, it means that that material is rather intact. That whenever there is a load on a point, it is likely to be on an intact material. Fractures are really not going to be present. So as a result, they found this out, that there is a negative exponential relationship between fracture spacing and point load test. Of course, in my own case, I want fractures to be very dense in the material. So whatever kind of load I impose on the rock, it must result in very dense set of fractures so that the strength of the material can reduce when that point comes to gouge out the fragment. Next, please. Next, please. Next. Next. Okay, so this picture that you see here, this sketch that I have drawn, shows how I would like to impose the impact. Whenever such an impact is imposed on the rock, what will happen is that there will be some crushing at the point of contact. That crushing will result in the reduction of the strength of the material. There will be cracks that radiate out at the point of impact. Please go to the earlier chart. Go to the earlier picture. Go to the earlier picture, please. I would like to illustrate with that. I know I have just about 5 minutes. Yes, as you see here, this is an illustration of the imposition of impact on a rock material. Because the stress that is imposed at the contact point is so high, material will be crushed. But beyond the crush zone, some radial fractures will result. So if I can impose this kind of load on the rock surface before the cutting bit comes around, it will significantly reduce the required cutting force. Next, please. Next, please. Next, please. Next, please. Okay, now, so I tested this with a number of rocks. I imposed some impact energy. The impact energy is measured in joules, from 5.56 joules all the way down to 72 all the way up to 72.31 joules. And I use Academy Black granite from Minneapolis, Lac Dubonnet granite, Sunset Red granite, and Rockville granite. As you can see from this table, point load resistance of rock reduces after impact. And it is most likely that the most effective impact is at 38.93 joules, where we can experience a very sharp reduction in the point load resistance. Go down, go down. Please, next. Next, please. Okay, and I also confirmed this through the use of sonic wave velocity. Because if you then measure the sonic wave velocity through the impacted area, there will be changes in that velocity as a result of the imposition of impact loads, as a result of cracks. So the decrease in sonic wave velocity was measured, and it was confirmed that in this, some cracks have resulted from that impact. Next, please. Next, please. Next, please. I'll take just 6 more minutes. Next, please. Okay, next, please. So we would like to look at how we can then introduce impact into mechanical excavators. My idea is this. If you look at an ordinary boom of a mechanical excavator, it is shown on the left. You see that that boom is shown on the left, and it would still rip rock. That is the normal one we have today. Currently, we have the one on the left that is demarked by A. The one on the B is my design, that we would have some impactors hit at particular points on the boom. They would hit. Those are hammers that you see there. The hammers are designated with 1, 2, 3, 4, 5. Those hammers would be hydrologically operated or pneumatically operated. That is, pneumatical operation is with air, hydraulic operation is with oil, hydraulics. Now, so the hammer would hit at that point, and that point would deflect. The chain would deflect, and the impactor would then hit the rock and cause cracks, much like what you saw earlier with the experimental setup. Then it would then be possible for this cutting bit that is next to that zone to remove large fragments. You see, the cutting bits are the ones that are in between the hammers. They would come in to excavate material that is already fractured, and the required cutting forces would be low. Let's go to the next slide, please.
Okay, Professor Inyang, you have 4 minutes left.
4 minutes, yes. I'll close in 4 minutes, yes. Next, please. Next, please. Okay, this is my idea, and this is now magnified. This is a section of that boom magnified. That, no, go back, please. Go back. Go back to what we just saw. Go back one. Go back one level. No, please. Go back. The next one. Okay, yes, this is the most important representation. In this representation, you see the impact points. Please move forward a little. Move forward. Okay, there is some sort of delay. So please move forward. Okay, this is it. You see the impact now fractures the rock. There is some level of crushing, but the important thing is that there are some radial cracks leaving the point of impact. Those radial cracks would be responsible for the drag bit that comes around dislodging larger fragments. This is precisely how machines should now operate those trenchers, so that they will reduce the cutting forces and then cut trenches faster. Now, this is a very big industry, because imagine pipelines crisscrossing Europe, imagine pipelines crisscrossing Africa, imagine pipelines crisscrossing Asia. So the significance of this is very large. They need to reduce cutting forces in machines so that machines can cut very fast, because at times these trenches can run for hundreds of miles to convey pipes, communication cables, and so forth. So 2 more minutes. I'll go to the summary, please. Go all the way to the summary. The final page. Go all the way to the final page. Yes. Now there are ways of arranging these booms and simulating experiments and so forth. So I think what should get out of this as a progression from this kind of research, those who would like to investigate this more, because I believe this has commercial value. Development and refinement of rock failure methods under high velocity impact, because that is dynamic fractures. It is much the same as when some sort of projectile hits some sort of brittle surface, the nature of deformation. Indexing of fractured zone size resulting at various energy levels. At some energy levels, cracking is accompanied by a lot of crushing, and the expenditure of energy in those modes of deformation are essentially different. Crushing takes a lot of energy. So certain types of materials will crush easier than others. Additional verification of reduction in drag bit cutting forces by induced pre-fracturing of rock. Development of a pneumatic cylinder system for loading and withdrawing of impactors on the rock surfaces. That's a mechanical engineering kind of thing. It's not really geomechanics. So in that case, the geomechanics researchers would need to work with mechanical engineers. The next one is development of synchronization technology for actions of both the impact bits and drag bits, because they have to hit and withdraw in the matter of seconds, so that the cutting bit can now come and impose its cutting action on the rock surface. Then development, finally, of quantitative tools, including models that combine machine and rock mass characteristics for pre-fracturing trenches that can be used in estimating rock trenching rate, energy requirements, and costs. I thank you very much for the opportunity, and I apologize for our inability to project this directly from here. So we will look for ways of doing that. Perhaps a return to Zoom will do. Thank you very much for your attention. I know that many people are listening from many places. I hope that the diagrams and the recitation were very clear. Thank you very much.
Okay, thank you. Thank you very much, Professor Inyang. Thank you for your excellent presentation. Because of the time limitation, I'm sorry we have no time for questions.
Yes. No problem.
Okay, now